good morning from Perth. And yeah, thanks again for the invite and for joining this. And I guess we're all interested in listening and educating ourselves how we can do better research, understanding better research, conducting research to then ultimately help clients, patients, or athletes by basically understanding what information to take in from science and probably which ones rather to ignore and omit, knowing that it could be based on biased or questionable research methods. So again, to start with, a little bit of housekeeping. This is Australia, the land down under. And here, this is Perth. And just to give you a bit of like understanding of the dimension, like from coast to coast, from west coast to east coast, it's about the same distance as the US-Canada border. So it's a pretty big land. And for me to travel to the next city, Melbourne or Sydney, takes me about 5 hours per plane. And Perth, where Edith County University is the most isolated city in the world. So we are here not quite fortunate to be amongst each other and enjoy beaches and the good weather almost throughout the year. And yeah, a bit of context to me, how this paper came along. Basically, to start with, my background, my trade is I'm a strength and conditioning coach by education. So basically, for the last 15 years, I was working, or I'm still working with athletes, supporting their physical preparation, writing their gym programs, their conditioning programs, just to make them physically as prepared as they can be for their sport. So this is kind of like my background. And 2 years ago, I graduated with my PhD here at ECU, more towards biomechanics and movement science. So trying to understand how people move and what we can do to change how they move in order to minimize the injury risk. And based on kind of like my sports science education, as you can guess, statistics is not my strongest field. And what I'll be presenting today was basically a fun side project throughout my PhD, which, however, wouldn't have been possible without the support and the guidance from Kristen Sainani and Sophia Nymphius. So as much as I'm going to speak about this paper, it was more so them guiding me, upskilling me about how to do better, how to read better meta-analysis, and then to be more attuned to what can go wrong, and then therefore be more skeptical with the results, the interpretation, and how we take this into context when, again, trying to help athletes, clients, patients in the real world. Bit of lessons from the past, at least for me, when I was trying to prep myself for this talk. I'm pretty sure we all seen this logo of the Cochrane collaboration, which features this forest plot. Basically a graph of the results from a very impactful landmark meta-analysis, which looked at an intervention given to pregnant mothers. Basically, when people give birth prematurely, as you might expect, that babies are more likely to die and suffer. And doctors in New Zealand had this idea to give a short, cheap course of steroids, and which might help to improve the outcomes. And 7 trials were tested, whether this idea is feasible and effective between 72 and 81, so many, many moons ago. And 2 of them showed some sort of benefits from steroid use, but the remaining 5 failed to detect any changes. And because of this, the idea just did catch on. And 8 years later, so in 89, a meta-analysis was done by pulling all the trials together. And just looking at this forest plot, we can see that there's a lot of not very certain studies, mostly crossing 0, but they're all a bit more towards the left. So they all seem to suggest that steroids might be beneficial, even if each study itself is not statistically significant. And guess what? The meta-analysis show that there's in fact a very strong evidence for steroid use, reducing the risk by 30 to 50% of babies dying unnecessarily from complication of premature birth. So probably, again, like we should always remember that the human cost of this abstract numbers. Babies died unnecessarily because they were deprived of life-saving treatment for over a decade, despite the evidence was already there. And we just haven't had the tools and the approach to synthesize this evidence. So just like a bit of like real world incidents, how meta-analysis can save lives. But again, from a sports science point of view, probably not that impactful with my work on a global scale. But still, having the right tools at the right time can help people all over the world. And yeah, so this basically brings me to the story of one outlier and how our paper came across. And we had this very influential and highly cited meta-analysis in our field in strength and conditioning, which was published about 10 years ago, which was basically looking at how much you can increase your squat strength in the gym by training, lifting weights, lifting heavier weights over time, and how that affects your sprint performance. Because as an outcome, faster athletes are more likely to succeed and be successful throughout many sports. So like a big question in our field is like, how can we make athletes faster? And just based on these results, it's a pretty clear statement, a strong and large correlation coefficient with a narrow bandwidth when we look at the confidence interval. So pretty much the conclusion and intervention is clear what to do to get stronger. But then when we look a bit more in depth, we see that one study or one effect size showed an improvement in sprint performance over 5 standard deviations, and improvement in squat performance almost 15 standard deviations. And then, common sense tells us that such an improvement are implausibly large. And indeed, the study that underlies for this effect size, which would translate like an increase in squat strength by about 110 kilos, which is probably 240-ish pounds in already trained athletes over an 8-week period. So which is highly implausible from a biological standpoint. And this was kind of like the kickstart for us to dive deeper in the underlying papers and just see what's going on and how those results came across. And then looking at this impactful meta-analysis, we find 5 errors that, made an impact on the statistical approach and the results. And we're going to talk about each of these more in depth, ignoring outliers, miscalculating effect sizes with standard error instead of standard deviation, ignoring within study correlation, failing to account within study variance, and focusing on within group rather than between group results. And those were the 5 big rocks that we captured in this one meta-analysis. And then we were like, look, if this one is already flawed, let's dive into the 20 most cited meta-analyses in our field and just check how many times at least one error was made. And kind of the shocking news to us, or the revealing information was that 80% of the 20 most cited meta-analyses in my field had at least one of these errors, which might or might not have impacted the conclusion. And as you can see, I put an asterisk to 80%. The initial publication was 85%, but then a couple of angry authors replied to us and tried to justify their work. And then turns out one of them didn't make a mistake, that we tried to do it, but the way it was written and described was, questionable. Anyway, so somewhere between 80 and 85% of the most cited meta-analyses seem to be flawed. And when we start with ignoring outliers, or an outlier in a meta-analysis or meta-regression can affect the validity and the robustness of the whole conclusion. And there's no single way of how to identify an outlier, and they're highly dependent on the context. However, some commonly used rule of thumbs are values that are anything more than 3 standard deviations from the mean, or more than 1.5 times the interquartile range from the median, is raising a red flag. And you want to be cautious about that and rather dive deep into the underlying paper to really understand where this is coming from. And after spotting such an outlier, researchers again should check first to make sure that the data point is indeed real and not an error. If it's an error, obviously you need to correct that. And if found to be true,
Then you can synthesize your data with and without this one outlier to estimate the influence of just this one paper, this one effect size on the overall conclusion. And yeah, there's different approaches how we can do that, different R packages that will help you to do this analysis with and without. And this is just like in hindsight what I saw after kind of like being attuned to like looking at outliers. And yeah, just a meta-analysis in a Q1 journal in my field. And they published a logarithmic risk ratio with a confidence interval of 662,451. I wish I had this confidence, pun intended, to submit and publish something like that. So again, something like that should raise at least an eyebrow to dive deeper into the underlying papers to see where this is coming from. But at least as we can see, this did not weigh in much to the end result of this forest plot analysis. Then the next one was miscalculating effect sizes using standard error instead of standard deviation. And just by confusing those two, you grab one without acknowledging what it is and then plug in it into your effect size calculation. And then, yeah, using standard errors rather than standard deviations when calculating effect sizes will artificially inflate the values. And using standard errors instead of standard deviation in the denominator causes the effect sizes to be massively overestimated. And just a bit of background, like standard deviation describes the variability of individual data points within one sample, while the standard error describes the precision of the sample as an estimate of the population mean. So the standard deviation is used to understand the distribution of data points, whereas standard error is used when making inferences about the population from a sample. And in cases where the underlying papers that you're using are only reporting your standard error, you can still easily derive the standard deviation by multiplying the standard error by the mean of the square root of the subject size by n. And then also, like, when I read and go through papers and see standard errors being used as a method to describe the data, it always feels to me like the authors are trying to artificially display a narrow bandwidth of uncertainty. And yeah, I still don't know why you would prefer standard error or standard deviation, at least in the studies in my field. And in our meta-analysis or in our review paper, we saw that like 60% of effect sizes more than 3 were due to a standard error, standard deviation mix-up. Next one, tying to that, yeah, still the effect size problem when we get the wrong numbers. And the errors often result in implausibly large effect sizes and overly narrow effect size confidence intervals, which are then highly conspicuous when visualized. And just to like get our head around like how big Cohen's d of 1 is, and this is visualized by our psychologist, cool page where you can play around with data points and visualizing them. And yeah, when Cohen's d equals 1, the difference between the two means relative to the variability within each group is equal to the pool standard deviation. And now when we go just to a effect size of 2, you see the massive change. And we saw in this paper like a effect size of 14. So you can't even plot that. That's how big those two means would be apart. And then after we identified the error, that it was indeed a standard error and standard deviation mix up, and recalculated the effect size, it went from 14 to 3. So a massive drop just by adhering to the correct way to calculate the effect sizes. Cool. Then the other one, ignoring within study correlation. And yeah, when performing meta-analyses, some studies may contribute more than just one effect size. And this can occur because of studies include either multiple intervention group or multiple measures per group. And a common error is to ignore these correlated nature of these observations, which can lead again to narrow confidence intervals and underestimated p-value. And I've highlighted them here in the figure.
basically you can see that the change in squat was the same across different sprint effect sizes. So basically what they did, they had a measure of 5-meter sprint performance, 10-meter sprint performance, 30-meter sprint performance, and they all chucked that in. And treating correlated observation as if they were independent can lead to an underestimate of standard error, resulting in artificially small p-values. And we need to account for that and adjust accordingly. And in this meta-analysis that we used as prime example, they used in total 15 studies, but reported 85 effect sizes. So again, telling me that there's multiple effect sizes going up at the same time, and we can't treat them as if they were independent. And we can account for correlated observation by using appropriate statistical models, such as like a multi-level model, to make sure we're not artificially overestimating our results and the conclusion. And this leads me to the next error, which is failing to account for within study variance. And in meta-analyses, studies are usually or should be weighted by the amount of information they provide, and such that studies that provide more information are weighted more heavily. And this is typically done by the by weighting studies by the inverse of the within study variance, or within group variance when there's multiple groups per study. And failing to incorporate this information just means the studies will be treated equally regardless of the size and the population size of the studies. So we want to weight studies that have a sample size of in the hundreds, way more than studies that are having sample sizes of single digits, 10, 15, 20, as most do within sports science. So attempting to pool effect sizes to perform meta-analysis or meta-regressions should pick appropriate statistical models that incorporate study weights and treat them differently when synthesizing the result. Then focusing on within group rather than between group results. Statistically, it is easier to find significant results using a within group comparison compared, of course, versus a between group course comparison. So testing one group at one time and then running intervention and testing them again is more likely to give you a significant effect versus using two groups at the same time and to see if the change in one group is actually bigger than the change in the other group. And many meta-analyses include controlled studies, but focus more on within group changes rather than between group comparisons. And again, this can lead to artificially inflated results. And by comparing to a control group, and this removes the effects that might have occurred regardless of the intervention, such as placebo. Ideally, at least in my field, we want to run two different interventions to see which one may be more effective or efficient, to then have a stronger conclusion for practitioners do intervention A over B, because something is always better than nothing. And meta-analysis should prioritize studies with control groups and should focus on between group comparisons rather than within group comparison, or at least have a separate analysis of these to see, hey, this is just my meta-analysis on within group, and this is my meta-analysis results on between group results when we're looking at certain effects, certain intervention, and treat them differently in our approach and then also in our conclusion. So after we found those 5 errors, we then obviously went along and tried to redo it in a corrected way. So we started by going to all the underlying paper and re-extracted data from all these 15 underlying studies. And because of this high correlation that I initially mentioned from accounting from correlated events, we kind of like neglected some of the effect sizes and only used one effect size per group to give us the biggest information. And this left us with 33 effect sizes instead of 85 to start with across 40 studies, because we couldn't extract and replicate the effect sizes from one study. And then we analyzed the data using our multi-level random effects model with nested groups. And yeah, as you can see, left is what was initially published, and then right is our results. And we note that there are still several data points that have surprising large effect sizes, such as like squad effects beyond if an effect size of 3. And although we are able to verify that these are correct values as calculated from the means and standard deviations, we cannot rule out that the presence of errors in the underlying data. For example, some papers reported standard deviations that are unexpectedly small for this given measure. That comes in where you need to have like context meta expertise to suss out, to evaluate if those values are plausible enough to include them in your meta-analyses. And then the reanalysis, our reanalysis did not change the overall conclusion of the paper, of the meta-analysis. It does moderate the conclusion. Initially, we had a correlation of 0.773, which represents a large correlation in which the majority, almost 60% of the variance in sprinting performance improvement can be attributed to increases in lower body strength or squat strength. Whereas what we found was a correlation effect of 0.56, which implies a moderate correlation, with only a minority, like 31% of the shared variance of sprint improvements can be attributed to improving your squat strength. Additionally, what was important to note that the confidence interval is much less precise in our reanalysis. So the width of the confidence interval in our reanalysis was almost tripled from 0.18 to 0.49, which is primarily due to proper accounting for correlate observation and the correct application of random effects, meta-regression accounting for between group and between study heterogeneity. So again, not a vastly different result, but different enough to moderate the conclusion and moderate the practical recommendations in our field. Which then again leads me to the recommendations and the learnings that I had from this paper. Again, starting with a Spider-Man quote, if with great power comes great responsibility. And with meta-analysis, we need to be very diligent and careful what message we are proposing. And then, the first one, you want to be very suspicious if the results are basically too good to be true. And this doesn't apply just to meta-analysis, but also to any experimental studies. If the results and the conclusion are very strong, very clear, you want to take a step back and like be very diligent with going through a paper and making sure that there's no biases or limitations that might have affected this conclusion. And again, anything beyond an effect size of 3 in our field is a good start to at least raise an eyebrow to be like, hey, what's going on? Then the second one, and we're not the first ones to voice that, we need to increase the transparency of the data, the underlying data that were used to conduct this meta-analysis. And then the more openly we can share it, make it accessible, it will be easier for other groups to redo the analysis and see if the values and the statistical approach, if the R script or the script has been published as well, and if we can then come to the same conclusion. And this is just going to help the field to be more transparent and do better in the long run. And the last one, again, something we're not the first ones to recommend that, but you want to seek statistical guidance with projects like that, and then understanding that meta-analyses are kind of like their own animal within stats. So you want to have someone with appropriate statistical understanding to guide you through the analysis part to make it as honest and true and transparent as possible, while not overestimating any results and conclusions. Then another learning for me, while kind of like diving deeper into meta-analysis throughout this time and like trying to understand what we can do better in the long run, is prediction intervals. And prediction intervals are a useful measure of uncertainty for meta-analyses that capture the likely effect of a new or a similar study based on the included studies. In comparison, confidence intervals reflect the uncertainty around the point estimate, but provide an incomplete summary of the underlying heterogeneity in the meta-analysis. So that kind of like teaches me, upskills my own BS radar when I read experimental studies, but know that the prediction intervals in this field, in this intervention, and makes me a bit more aware and aware of how the spread of the effect sizes of individual studies may look like. And then everything that is beyond or under this effect sizes, again, you might want to raise an eyebrow to see what's going on and really dive into this study. And this is how it's visualized. Then again, I'm not the first one, or we're not the first ones to recommend this, but sports and exercise scientists or researchers in general should embrace intellectual humility and acknowledge the inherent uncertainty of their work. Basically, you want to be the biggest critic of your own work, because only you yourself know how to best poke holes into the conclusion of your research paper. You know best where the limitations lie, starting from study design to data acquisition, analysis, interpretation, and conclusion. And we can always do something better at any step, I'd say. And basically, we want to embrace our inner Karl Popper and try to falsify our own work as much as we can to do a better job in the long run. And then transparency about flaws and limitations rather fosters humility while concealing them. I feel like it breeds overconfidence, arrogance, and intellectual fragility. So again, everybody who is like very confident in their results and interpretation that something is very black and white, again, something you want to raise an eyebrow, take a step back, and reevaluate. So basically, this brings me to, it's not the tool that should be criticized, as in this case, meta-analyses. And in the case, the analysis was not done appropriately. Again, with this example at the very beginning, how impactful meta-analyses can be in life or death situations. We want to make sure that the tools we use are used appropriately so we can draw the correct conclusion and help the population in the long run. But again, just because our statistical approach is correct and accurate, we still need to have enough context matter expertise to evaluate the quality of the underlying papers and to not kind of like lead into this fallacy of garbage in, garbage out. And this is, again, something that's not new issue in not just our field, but there's a suboptimal adherence to recommended practices on methods, quality, and reporting standards, not just in reviews and meta-analyses within physical activity, but also in the underlying papers. So again, something to be very mindful of when we read studies, what the quality of the study is, if they adhere to recommended guidelines or not, and therefore moderate the results when you either just read an experimental study or use it for a meta-analysis. So in hindsight, after we published the studies, and me being an early career researcher, still getting very excited about every citation that comes out of my publication, a couple of papers that cited this paper who tried to kind of like redo or recheck other meta-analyses and the conclusions they made. So this one is on vitamin D supplementation, and just by adhering and acknowledging those errors, redoing the meta-analyses in a less wrong way, what they found that a strong effect size, a strong conclusion was indeed moderated after accounting for these errors from 0.75 to 0.16, which is a huge change. Then another study that only looked at the standard error and standard deviation mix up, and this was in some sort of conditioning endurance intervention. And they came to the conclusion that same thing, a strong, big effect size was moderated and almost reduced by 1/3 in both cases. So again, just adhering and acknowledging simple guidelines can have a massive impact on the result and the recommendation of meta-analyses. So again, this leads me to kind of like the first kind of like mini conclusion. You want to make sure that when you do a meta-analysis, you want to adhere to the correct approaches, understand the limitations and understand the pitfalls before you like come up with your conclusion and seek statistical guidance. Then you also need to have enough subject matter or context expertise to be able to understand the quality of the underlying papers that are informing your meta-analyses and which may or may not moderate the conclusion. And then, if best case adhering to those two big boxes, meta-analysis will indeed help us design better primary research and produce useful and actionable recommendations in the long run. And something that we all know and are aware of, if study quality and statistical approaches are inadequate, it only increases the chance of the next replication crisis, which room on the street in sports and exercise science is probably a massive issue. And we all need to do a better job in conducting better experimental studies and meta-analyses to provide a benefit to the population, to our population at hand. So basically, last slide, don't need more research, we need better research. By understanding the limitations, understanding our limitations in our own work, and then seeking guidance, seeking support in order to make us aware of where the pitfalls might lie, and then do better in the long run without overestimating our effects of the interventions on meta-analyses that we provide and propose. So that's kind of like my journey, my learnings throughout this one paper that we conducted, and in hindsight, what emerged out of that. And I hope you got something out of that, and happy to answer any questions or start any conversation that might stem from this. Thank you.
Thanks very much, Dan. That was great, actually. Okay, so Guillaume asks, very interesting. So how can we spot these errors on the forest plot? I actually had a similar question too. So, or funnel plots or other tools or tips to identify like the errors that you said more easily. Because a lot of time, we go through these papers and it's, one of the harder ones is within study variants or between study variants. And how do we know if they've done that properly? But back to Guillaume's question.
So let me share my screen again, and I'll show you some of the figures that we put in our paper, where it's very easy to spot those outliers, at least those two big errors that you can conduct, and which may moderate the results quite sufficiently. So this is our paper, and then these are actual figures from studies that we used, and just by looking at those outliers, those effect sizes which are just implausible in our field, are like, that's kind of like your first red flag within meta-analyses. it's like something is going on. Like even the basic
Yeah,
steps
definitely.
were done insufficiently. And that's where you then might start diving deeper into the methods and be like, okay, if that's already such a suspicious error that wasn't picked up by the authors, editors, and reviewers, then chances are that there's more going on. And then, yeah, that's when the real work starts and understanding, okay, what meta-analytic approach did they do, and what underlying studies did they incorporate, and how did they treat interventional within group and also like between group analysis. And this, yeah, not gonna lie, this is hard work, just going through all those underlying papers, trying to understand that. And yeah, this project took us almost 2 years from the first idea to the final publication. And yeah, I still say and argue just by adhering and visualizing those effect sizes can give you at least enough indication to like, okay, do I really take the result and interpretation of this meta-analysis at face value and let it inform my practice, or I put it into the basket of like, yeah, cool, good luck, try again.
So what does a normal person do? Like, you know what I mean? Like, who doesn't have a methods background? Like, if they saw something like that, is there like maybe an AI tool, or is there people like, you know, on Twitter or any other kind of, you know, academic forum, maybe like Slack, channels, or is there somewhere people could go to say, hey, listen, I think this, you know what I mean? This meta-analysis or network meta-analysis, whatever it may be, is I think a bit fishy. Can somebody look into this? Is that possible or not? Not currently.
So the way we got about that with my supervisor and mentor, like we reached out to Kristin Sainani, knowing that she has a very strong and impactful background, and be like, hey, we tried our best, like we feel something is going on, we can't exactly pinpoint it, and like, yeah, reach out to experts with the hint to be like, hey, we just want to know better. And like, again, usually in this field, like we are all trying to do better and help each other, and then like just starting this conversation in this way. And yeah, I have come across now about any like AI tools or like platforms where you can like chuck that in and it tells you what the potential errors are or not are, which probably might come in the close future, the way how AI tools are evolving. But yeah, for now, still meta-analyses are hard work to go through that and like publish something that is meaningful. And then like to check them is even harder work. So yeah, probably there's no shortcut in how to get better at that other than like sitting down and diving into that. But again, like our recommendation, just like those obvious errors are like a big enough red flag to raise and increase your trust issues.
So I actually had a comment. I think one of your slides, you said the results of the conclusions. I can't remember. I'm trying to find it. Actually, I took a picture. I think it was like, yeah, ignoring outliers. So you said an outlier in a meta-analysis or meta-regression can affect the validity and robustness of the conclusion. And so here, I think bias, I think you're getting confused about, so there's two things: bias in the results or the effect estimates, and then there's also bias in the conclusions. And those are two very different things actually, because as you know, you get the effect estimates, and of course those could be manipulated and maybe, you know, purposefully in the ways that, you know, you like outlined. I mean, they're probably, I mean, I don't know what you think, but hopefully like they're mistakes. Um, but I mean, once you have those effect estimates from your meta-analysis, I mean, the way to interpret it would be to, you know, use the risk of bias of all the studies and then look at, you know, some of the limitations of your own meta-analysis. Say, for example, you know, you didn't search for, you know, all languages. So potentially you might have missed studies, you might have missed some, you know, effect estimates that could have gone in your meta-analysis. So that's one of the limitations of the meta-analysis. And then you look at the risk of bias, and then that that could inform your conclusions. And so there could be bias in the conclusions because the authors may not have taken into account the bias and the limitations of their own meta-analysis. However, the bias in the results is kind of a different thing, because you can actually, you know, as you very well know, overinterpret, you know, the results in your conclusions.
And yeah, and that's a challenge we researchers need to embrace, and again have this humility in not overstating our own results, which it's very hard for me as well, especially as an early career researcher, to be like, oh, if I found something, there's an asterisk, we have significant results in trying to like overestimate it. And then like, yeah, my mentors and co-authors are like, yeah, come on, sit down. Let's talk through it.
So anyway, so the other thing too that we find is that in my research too is that you find that when a meta-analysis and a systematic review, they say that they're gonna look at all these outcomes, but in the end they only report the statistically significant outcomes in their paper without mentioning the other outcomes at all. And so we really want, when we're looking and interpreting the results, we want to have a balanced conclusion where you kind of look at all the outcomes, no matter whether they're statistically significant or not, or not in the direction that you want, or not as large of a, magnitude of effect that you want. So yeah, you want to just be like fair to everything, all the analyses that you've done.
Absolutely. And that, yeah, I couldn't agree more. And that like requires a lot of work and a lot of expertise, humility, to not wanting to have like this super impactful, shiny, almost too good to be true results, and yeah, state it for what it is. And that's probably something we can all do better and have to do better to help the people with our research.
Yeah, I had another question too. So you said at one point that, in some of the systematic reviews with meta-analysis, that they had a lot of effect estimates that you could have chose from. So how did you create a decision rule to decide, okay, so we're going to use like this outcome, or did you arbitrarily like pick it?
So in our example, when the underlying papers used sprint measures of like 5, 10, 30 meters, which are highly correlated. When we ran an ICC, it had like a 0.96. So it basically gave us the same information across all of these. And then we always chose the longest sprinting distance as a true proxy of sprinting speed, and yeah, disregarded all the other ones before that. And that's kind of like how we got about that. Understanding the like sprint performance is probably something is different to acceleration. So that's where your subject matter expertise comes in. And then to be better able to like, yeah, I'm going to disregard this, I'm going to focus on this, because I know this is important in my field and has the biggest impact and overall outcome on interventions, treatments, or whatever. So yeah, that was kind of like our approach, informed by our practical and lived experience.
Okay, great. Thank you. So in your opinion, do you think people did any of that on purpose? Like, was there like any paper where you were like, very suspicious, or no, you think it was just by accident?
Benefit of the doubt, and 100%, like no one wants to like present flawed or consciously flaw your results and change your results just to like drive your research in a better way. And probably also that like a lot of systematic reviews and meta-analyses are done by PhD students, which just don't know better and have insufficient guidance and mentoring around how to do those inherently complicated analyses in the best way. And that's probably like one limitation that we need to address, that like, yeah, you need to be a very expert in this field with this statistical or methodological approach to publish something that is meaningful, and not let it your first year PhD students conduct. So that's kind of like what often happens in our field and is like a big point of critique.
Oh, really? Okay, right. Yeah. So Guillaume is asking, any idea if it gets better with time? So if there's more recent meta-analyses that have less errors, or have you looked at that?
Yeah, so again, trying to be the biggest critique of my own work, the 20 most highlighted meta-analyses in our field that we use to compare it, again, being highly cited is a matter of time. So they have been already published 10, 15 years ago. And it just as if everybody reads their own papers from 10, 15 years ago, I think we all cringe on that, what the methods were, or like how we interpreted that. So yeah, of course, there's an evolution. It's getting better with people being more literate with coding, are using packages that can like account for a lot of those errors and issues. It like definitely got better. The way those meta-analyses that I read now is like, yeah, it's the approaches are getting better. Yet those outliers, mixing up standard errors and standard deviations, that's something no package can pick up, but you need to be aware of those differences and educated enough to be like, yep, I need to change that value into something else. Otherwise, I get an error. And vice versa, to have enough subject matter expertise that if you see an effect size in your own results that's 3 or higher, to be like, oof, that can't be. So again, challenging yourself. But yeah, I feel it is getting better, but we still need to have enough expertise and experience to minimize as many errors as we can, starting with the easiest.
Great. And so what research are you working on now, Dan, and what's like coming up for the future?
So yeah, I hope we can kick on this and like try to redo these underlying meta-analyses that we pinpointed might have been insufficiently done, but more so like I'm more into sports science and human performance, trying to understand how humans perform, move the way they do, and what we can do to change that more from like a biomechanical 3D motion point of view. So another nerdy area that I'm interested in, and yeah, still having a very soft spot for like stats and how to read better and do better research.
Wonderful. Okay, well, does anybody else have any last comment or question? Well, if not, I'd like to just thank you again for presenting. It was a great presentation and one where we've wanted to hear more about the errors that are common in meta-analysis. So thank you again for presenting for us, and hope to see you maybe in the future again.